Next up, we've got our final technology presentation from Scientific Aviation. Stephen Conley is the president and CEO of Scientific Aviation, an airborne scientific research company that specializes in atmospheric measurement and the quantification of methane emissions. EDF have actually worked very closely with Stephen and his team on methane quantification studies, the Permian MAP project being one of our most public ones. A reminder again, just keep on using that Q&A function and we'll have a chance to ask Stephen some questions. Okay, Mr. Conley, over to you.
Well, thank you. So Scientific Aviation, we basically have three products that we have that are sort of relative to this space. The one that we've used the most of in the past is our manned aircraft. And what I want to do right now is sort of just give you the quick overview of when each of these products sort of is a good fit. For the manned aircraft, what they're good at is covering large areas sort of quickly. So with one of these manned aircraft, we can typically survey about 800 square miles in a day. So that can be useful either like EDF has used it in the past to figure out what's the total emissions from a basin, like how much gas is coming out of the Permian Basin in total. The other thing it's really good for is doing sort of quick surveys just to look for super emitters. So one thing about the super emitters is that we've seen over the past, I'd say 7 years, now a number of studies that have all shown the same thing, that if you want to reduce the total emissions, it's the super emitters that count. You know, something like the top 5 or 10% of your emission sources contribute more than half of the total. And so hitting those emissions, the large emission sources fast is like the best thing you can do to reduce the total. So that's where the manned aircraft are handy. Now the unmanned, the drones came to being because we needed a super accurate way to get a total emission number from an individual site or even an individual component on a site. And that was always a challenge with the airplane because it's turning like a 1 kilometer circle and you might have 2 sites within that circle, which is where the drones come in, that they can get as tight and as close as you want. So with the drone, the other advantage of the drone is that that's something that the operator can actually use themselves, where the aircraft, obviously we have to send pilots because it requires a higher skill level. But like one of our clients right now is flying the drone, and they just spent the week training one of their own people to do the drone flights. And then they can go do these drones and they can either upload the data to us and we can give them back their quantification, or they just do it themselves. So that's the first 2 of our systems, the manned and unmanned. And the problem both of them sort of suffer from in terms of cost is that they both are people intensive. Like they get you a measurement at a point in time. And so one of the issues you come up with is if you're trying to increase your frequency and you're doing these things at a point in time, that can add up quickly in cost. So that's where the continuous monitoring system comes from. That the idea of this is that it's just monitoring 24/7. It's always looking. When you have a sort of larger emission source, and by large, I mean like 50 scuff per hour, 1 kilogram per hour and above, that these systems will detect that. And then in addition to detecting, typically when we outfit these on a site, we'll have more than 1 sensor on a site, which then lets us do triangulation. So if they do sense something, we can actually sort of locate where it is. It's tank number 1 or it's the flare. So those are the 3 different systems that we offer. And just to kind of give you an idea of where Scientific Aviation as a company has taken these systems basically all over the world. So we work a lot for operators, regulators, NGOs. We last summer flew for the United Nations in the North Sea in Romania. So these planes have been well vetted, and the drones as well. They're published. And actually the event that kind of put us on the map was the Aliso Canyon disaster back in 2015. Initially, everybody knew there was a leak, but no one knew how big it was. And so that's after 2 weeks, the state of California sent us on site to actually quantify it from the aircraft. It ended up being the largest methane leak in US history and was published in the journal Science. So the kind of the point is that the numbers that come out of the aircraft and the drone are sort of well verified. They've been published in peer-reviewed literature. And we use that same methodology that the plane uses in the drone and as well in the continuous system. The big difference is that with the continuous system, instead of us moving through the plume like we do in the plane and the drone, we sit still and let the wind move the plume through us. So it's just a subtle difference, but all three systems end up with one thing in common, that what they look at is actually calculating an emission level. So as opposed to just telling you there's 3 ppm of methane, the idea with these is that they will actually measure the amount of methane, like in kilograms per hour, coming out of a site. So this just gives you kind of a picture of how it looks. So this is actually a real flight in a real facility over on the right here. And what you can see is that the wind here blowing from the northeast and you have these red areas on the northwest, and the southeast, you see the red high levels of methane. And basically what the plane or the drone do is you fly from below the level of the plume, say 200 feet above the ground, up to well above the level of the plume. You just add up the total amount of methane that comes in and out of your circle, and that gives you the total emission from the source. So like I said, all these techniques have been published now. So this is where it gets interesting. So what happens is with the planes and the drones, you're typically getting, like Matt mentioned, a point in time measurement. And so there's always this question of what's happening the rest of the time. Great example, last week we're flying for EDF in the Permian and we stumble across a 12 ton per hour source. You think about that, that means in 1 hour, that's the equivalent of 200 vehicles driving for a year. So it's a really big source. Now, whether that leak started 5 minutes before we arrived or 5 months, we don't know. All we know is that when the plane got there, we can see it going. In fact, that you can see in this image that it was actually visible on the visual camera, not just on the infrared. We did get infrared image of it as well. But so the thing that's important, that what that points out to us, is that a leak like that is really expensive for an operator for many reasons, like lost gas, whatever might happen on the regulatory side, the PR side. There's just a lot of avenues where that can be costly. And the problem is, how can you increase your frequency without driving up the cost? Because the EPA estimates each time that you send a FLIR camera crew to a site, you're talking about a $600 cost. Similarly, the drone is a little bit less, but it's in that same ballpark. And the plane is also up. It's less than that, but it's still, every technology that we send is going to have a fairly substantial cost. This is where the continuous monitoring comes in. So here's a system that's about $30 a month, but what it's doing is it's constantly watching. So if one of those, like a leak that size especially, you would have known that within 15 minutes. And so the idea with this, with the continuous system, and not just ours, but every continuous system on the market, is that the goal of them is that they help you to find your leaks, or operators to find their own leaks before EPA or EDF, before somebody else does it for you. So that's the basic idea of these continuous systems. And it's sort of, in a way, it's that security that that, like, if TCEQ has a plane going or a helicopter flying with a FLIR camera, you'll have a little bit more security to know that they're not going to find your flare out, because if it was, you would have found out about it yesterday. So that's the idea. And that kind of brings me to there's one difference with our system. In fact, our company being a bunch of atmospheric scientists, most systems that are on the market today on the continuous side are measuring the methane concentration. I like to show this plot. This is real data up to today. And what you can see, if you look at this plot, the blue shaded line here is the wind speed. And I've kind of put arrows every time the wind speed drops. But you'll notice every time the wind drops, the methane jumps, every time. And that's nothing magic. That's just because the wind acts as sort of a flushing. It brings clean air in and flushes out the sort of methane-rich air from whatever sources are on the site. But what that means is that if your system that you deploy is relying on the methane concentration or the VOC concentration, that every time the wind stops, you're going to get a false alarm. And like we looked at earlier, every time you send a crew out, that's $600. And so the reason that we, on all of our systems, look at the actual emission rate is that by combining the methane and the wind and the atmospheric stability, you take that out of the equation. We're not going to send you on a false alert because the wind stopped. We still might have false alarms, but they're going to be caused by, we didn't know that somebody on site was depressurizing a tank, or there was a truck, or whatever. But we're not going to be having an alert caused by atmospheric conditions. So this was kind of exciting. 2 weeks after deploying our first of these, which was back in February, we deployed the first 8 in Texas. And we had four sensors monitoring this central processing facility on the south here. And to the north, we had just a standard well pad. And on one evening, about a week after deploying, sensor number 1, in the top left corner here, picks up an emission with winds out of the east. And then 3 hours later, sensor number 3 picks it up with winds out of the northeast. And what the system does is it triangulates. It doesn't care whether it's on or off site. And so it generated an alert for the flare on the adjacent facility. And so the operator sent out a repair crew and discovered that what they explained to us was the flare gas pressure was set too high and was just causing the flame to blow out. But it was really exciting that the system not only detected the leak, but detected it on a site we're not even monitoring. That's the other point, that these systems don't need to belong to whatever site they're on. They'll protect whatever's nearby. So last thing I want to show you is sort of just the scale, how we sort of see these systems all playing together. That as you move down this chart on the left, you go to higher costs and you go to sort of higher accuracy at the same time. So at the highest level, you have like satellites looking down, the largest leaks, then aircraft, similar price, smaller leaks, drones, much smaller, about 3 orders of magnitude better when you get down to the drones, the level of leak they'll find. And then cameras similar in precision and leak size to the drones, but also offer the benefit of pinpointing where the source is. So all of those are sort of the point in time measurements. And then on the right here is the sort of continuous system, more of a monthly cost, but you get these results immediately. And that's all I got for you.
Great, thanks, Stephen. I think we've only got a chance for 1 or 2 questions, but someone from the audience asked if the operators can utilize the drone option without having an FAA drone license.
No, they do need the drone license. And that's what the other operators that have done this have done, is it takes about 40 hours to get that. So typically they'll have whatever operator they want go through that process of getting the FAA Part 107 license.
Okay, and the second one, if we go rapid fire here, like what determines how many ground sensors are required for a given site?
2 things. So one is how large is the site. So basically what we look at is how much the wind is varying. We want to try to have, it's basically a time to detection question. So on a typical site, like on one of those central processing facilities or central tank battery, probably put 4 sensors on it so that we cover all the wind directions. And then the other thing is how much that site is a concern. So like, is it right next to a school? Is it out in the middle of nowhere? Does it have the capability for a large leak? Like some sites just don't have high pressure gas. You can't even get a high pressure leak. So those might not be worth any sensors, or maybe just 1 sensor. So we basically would put that together, those kind of things together to get that.
Well, great. Stephen, we've got some other questions from the audience, but perhaps I'll send them to you offline and we can send the answers out as part of our resources material afterwards. But I want to thank you again for coming today and delivering that great presentation.
Wonderful, thank you.